So typically at the end of a section, I go back and I look through all the homework and I look at our quiz and all of that, and I make sure that everything that you need to know is covered in one of the videos. And often there's a few things that I'm kind of like, I wish I would have added this or that or done this a little bit differently. And so I often make one more video towards the end. This is that one more video. I should be able to keep it pretty short. I just want to get through a couple of examples, remind you of some stuff and highlight some stuff, and then we'll really be done with the chain rule. So this first problem, the idea here is to find f prime of 3 where our function f of x is as given up here. Maybe at this point in the class you could figure out this derivative without any color coordination or anything. A good first step if you were looking at this problem is to recognize that you have a cubed root here. And we don't directly have any rules for taking the derivative of cubed roots, but if we rewrite them in exponent notation, so instead of the cubed root of the natural log of x squared minus 8 cubed, we have the natural log of x squared minus 8 cubed, all raised up to the 1/3 power. I think I have all my parentheses in the right spaces here. Now for the calculus part, our first step is to recognize that the outermost function is the stuff being raised up to the 1/3 power. I'm taking the cubed root of all of this stuff. So first I want to deal with this 1/3 power right here. Using my power rule, I bring that 1/3 down in front, leave everything else completely alone, and then subtract 1 from that exponent. 1/3 minus 1 is negative 2/3. I'll copy down all that stuff that I wanted to leave completely alone, the natural log of x squared minus 8 cubed, and then recognize that I'm not done. I still have to multiply this by the derivative of all that stuff. Again, the natural log of x squared minus 8 cubed. Frankly, if you can get this far, you're probably going to finish the problem. It's kind of once you get started, you're in pretty good shape. This is all done. There's no d over dx symbols here. And for this part, maybe I could recognize that I have another chain rule here. I'm taking the natural log of something. The derivative of natural log of x is 1 over x, so the derivative of the natural log of all this stuff is 1 divided by all this stuff, in this case x squared minus 8 to the 3rd power, times the derivative of all that stuff, again, x squared minus 8 to the 3rd power. In this top line, I kind of took care of my first layer, the exponent of 1/3. In this next line, I took care of the next layer, this natural log. All that's left is this derivative over here, which, if it wasn't hidden inside all this mess, wouldn't be too formidable of a task. It's a little bit intimidating to see it with all this other stuff, but if you just focus on this stuff, the derivative of something cubed, that's easy. Just recognize that there's one more layer of the chain rule. I got some stuff, x squared minus 8, raised up to the 3rd power. The outer function is the raised up to the 3rd power part. So I want to use the power rule to bring that 3 down in front, leave all the stuff alone, and have an exponent of 1 less than 3, in other words 2. That stuff that I'm leaving alone is x squared minus 8, and I'll be done once I multiply that by the derivative of that stuff, the x squared minus 8. Copy all this stuff that I'm not messing with at all because it doesn't have any d over dx symbols. It's all done in a sense. And just figure out this last derivative. The derivative of x squared minus 8 is just the derivative of x squared minus the derivative of 8. And the derivative of x squared is 2x. The derivative of 8 is 0. So I get 2x as my answer. This huge product right here is my derivative. You could absolutely clean this up if you felt like it. There's a few things that jump out to me, that I have an x squared minus 8 squared up in the numerator and an x squared minus 8 cubed down in the denominator. So those could certainly cancel. I got a 1/3 and a 3. Those could cancel. I think I could clean this up significantly if I felt like it, but I don't feel like it. The other comment that I want to make is, you'll get to a point where you don't need to show 4 lines worth of work for this. It's not a bad idea to show the 4 lines until you're really comfortable, but later on when you're doing these, you'll stare at this derivative, recognize that the outermost layer is the 1/3, take care of the 1/3, and then be like, all right, and now I have to take the derivative of everything here except for the 1/3. So my next layer is the natural log stuff. And you'll take care of that natural log layer here. And you'll be like, all right, I'm making lots of progress. My next layer is this stuff raised up to the 3rd power. So you'll take care of that 3rd power here. And then you'll be like, oh, finally, I got all the way down to the middle of this, I don't know, onion or something. So I take the derivative of the innermost layer, which is this 2x. If you're not already there, it won't be long till you get from here directly down here in one step. But for the sake of tutorial videos, I kind of feel like I should show all the different steps. So each time I applied the chain rule, I wrote a different line here. The other comment that I want to make is, if you teach math for a living like I do, you might recognize that we're taking the log of something cubed. And when you're in that situation where you're taking the log of something cubed, there's a log rule that applies. Maybe you remember from a different class that the log of something raised up to a power is that power times the log of that something. These aren't derivatives. This isn't the power rule going on here. This is a log rule that you learn well before calculus that just says that this happens to be exactly the same as this because of some interesting properties of logs. That log rule would have come in a little bit handy here. It would have allowed us to get rid of this exponent here to make it a coefficient. And if you're thinking about derivative rules, if it's a coefficient, it's really easy to deal with because the coefficient derivative rule was really simple. It essentially says ignore the coefficient. But if you leave it as an exponent, that's a whole nother layer of the chain rule that shows up in here. The reason this answer simplifies so nicely that a lot of these x squared minus 8s cancel out with this x squared minus 8 is because we could have used this log rule in here to rewrite this thing algebraically to make the calculus a little bit easier. And you're like, I guess, but that would have made the calculus that much easier, and it would be relying upon me, the student, recognizing that I could have used this log rule, remembering every single thing that I ever learned in a previous math class, which is not at all reasonable. Definitely not for the minimal payoff that we'd get in this problem. And that's true. However, there are instances, like this problem down here, where if you use log rules, it's going to make your life a lot easier. So one of the things that I wanted to tack onto this video is reminding you of 3 different log rules. The one that's written up here already, the fact that the log of a product is just the sum of 2 different logs. And if you kind of put these log rules together and use some clever algebra, you can come up with the fact that the log of a quotient is equal to the difference in 2 different logs. Taking things that look like the left side of any of these equations and changing them into the right side of any of these equations can make the calculus a lot easier. So even if you didn't remember these log rules coming into this class, maybe they're worth writing down somewhere. And when you're doing calculus and it feels like a harder problem than maybe it should be, it might be worth considering using these different rules. But before I move on to the second example, I should point out that I haven't answered this first question yet, right? This question didn't ask me to find f prime of x. What it asked me to find is f prime of 3. What I found down here is the derivative of this expression. So this down here is f prime of x, which is not what the question is asking for. The question is asking for f prime of 3, and that was intentional. The reason I wanted to ask for f prime of 3 is because a lot of homework questions ask for f prime of 3, and a lot of my video examples just show you how to get f prime of x. I often don't do this last step because it's a little bit tedious, but sometimes you have to in the homework. So just in case you've forgotten, if you're asked a question like this, make sure you first find f prime of x, then change all the x's into 3's. I think in this case, doing so will allow this to simplify really nicely. As a first step, I'm copying exactly what I see here, changing all the x's into 3. That gives me this purple line. For the sake of the homework, you could type this purple line into a homework system, and it would mark it as correct, but we might as well simplify because things are going to work out so nicely. Why does it work out so nicely? Because 3 squared is 9, and 9 minus 8 is 1, and 1s, loosely speaking, are really nice in math. Look what happens here. I have this 1/3, and then I'm taking the natural log of 1 cubed. But wait a minute, 1 cubed is just 1. So I'm really just taking the natural log of 1. When I figure out what that is equal to, I'm going to raise this to the negative 2/3 power. I just realized that I didn't make a great example here, but whatever. I'm going to plow through. I'm going to get the answer, and then I'm going to show you why this wasn't a great question to begin with, and maybe beg for your forgiveness. Anyways, over here I got 3 squared, which is 9, and 9 minus 8 is 1, and 1 cubed is again 1. Over here I got 3 times, 9 minus 8 is 1, and 1 squared will end up being 1. And then I got 2 times 3, which is 6. I got 1/3, the natural log of 1, raised up to the negative 2/3 power, times 1 times 3 times 1 times 6. 1 times 3 times 1 times 6 is just 18. So I got 1/3 times 18, in other words 6, times the natural log of 1, raised up to the negative 2/3 power. Problem: the natural log of 1 is 0. Because the natural log of 1 is asking you the question, what power do you have to raise e up to turn it into a 1? And because e to the 0 power equals 1, the natural log of 1 is equal to 0. And you're like, oh, cool, I like 1s, but I like 0s even better in math because that really makes stuff go away. Well, often yes, but in this case, no, unfortunately. Because I have this negative exponent, what this is asking me to do is take 1 and divide it by 0 raised up to the 2/3 power. That's problematic because 0 to the 2/3 power is 0, so I get 6 times 1 over 0, and 1 over 0 is undefined in math. So really, this was a terrible question to ask you for f prime of 3. I really should have asked you for f prime of x, and we could have stopped right here. I wanted to remind you how to come up with the answer for f prime of 3, and I wanted to make the math work out really nicely. So I kind of looked at this really quickly without thinking too deep about it, and I was like, oh, 3s, students will love that. But unfortunately, when you go plugging in 3s, well, you kind of get a bad answer. But don't let that dissuade you. The reason I'm going to keep this example is I want to remind you how to evaluate f prime of 3, and here's how you do it. And if you're ever asked to do it on a quiz or homework or something, you'll end up getting some number, probably a pretty nice number, as your answer. On this one, I screwed up and made the answer undefined. I accidentally made you divide by 0, but whatever. Hopefully the point remains. This example was supposed to be a really, really hard chain rule problem. I think there's 4 layers of the chain rule going on in here. Hopefully this is a little bit of review from the last video where we did the really hard chain rule problems when they were nested inside other chain rules or various rules. That got us f prime of x. And then this little reminder how to figure out f prime of 3 that didn't work out really well, but maybe you'll let it slide. And then a comment about these log rules, which we didn't even end up using here, but I think you'll find them really useful when we do the second and last example of this video. We're given this function g of x. What we're asked to figure out is g prime of x. It sounds easy enough. And then we're asked to figure out g double prime of x. And then there's this little hint that says use log rules. Because you don't need to use log rules to figure out this problem, but it'll make your life so much easier. What I want to do is figure out the derivative of the natural log of x squared e to the x raised up to the 1/2 power. I'll try to make my parentheses different heights so you can see what corresponds with what. And notice that I changed this square root into the 1/2 power because I know that exponent form is more conducive to my various derivative rules. You could just start plowing through this right now if you wanted. The outermost layer would be the natural log, the next layer would be the 1/2 power, and then the final layer would be this x squared e to the x thing where you'd have to use the product rule. You could absolutely do that, but it might make more sense to do some algebra before you do any calculus. Leave the derivative stuff alone. Let's just mess with what this thing is equal to on the inside. I'm taking the log of something raised up to the 1/2 power. This log rule says anytime you're taking the log of something raised up to a power, you can bring that power in front of the log. Don't confuse this with the power rule. This is a log rule that allows me to say that the natural log of x squared e to the x to the 1/2 power is the exact same as 1/2 times the natural log of x squared e to the x. No calculus yet. And in this next step, I'm going to continue to not do calculus. What I'm going to do in this next step is recognize that I got the natural log of something times something, x squared times e to the x. So I go up here to my log rules and I recognize that anytime I got the log of something times something, I can rewrite that as the log of the first thing plus the log of the second thing. So down here I can replace the natural log of x squared times e to the x with the natural log of x squared plus the natural log of e to the x. That's a great thing to do. We don't like, generally speaking, products in calculus because you got to use the product rule. We love sums in calculus because the derivative of a sum in calculus is just the sum of the two derivatives. We can just break this up into 2 easier problems. At this point, you're probably ready to do some calculus, and you could if you want, but I'm not going to. I'm going to look at each of these logs and recognize that in each case, I'm taking the log of something raised up to a power again. I'm back up to this rule. The log of something to a power is that power times the log of whatever the base was. So the natural log of x squared can be rewritten as 2 times the natural log of x. And the natural log of e to the x can be rewritten as x times the natural log of e. You don't have to do this. At this point, it's probably simple enough that you could just do the calculus. But I want to make really clear the advantages of using these log rules and simplifying these expressions before you use the calculus, because you'll see it'll save you lots of steps, which is not just a lazy thing, but it's an efficient thing. If you're good enough with this algebra, you can make it way less likely that you make a little mistake doing the calculus. Couple of things here. From this line to this line, I changed a product into a sum. When I changed this product into a sum, I had 2 terms inside these parentheses. When you have 2 terms, you got to be really careful. If I didn't have these parentheses written here, this 1/2 would only apply to the first thing. It wouldn't apply to both of them. I really need these parentheses. And I know that a lot of students would leave these parentheses off, which is why I want to make such a big deal out of this. This 1/2 applies to both of these terms because this 1/2 came from this 1/2, and this 1/2 was an exponent on both of these factors. If you wanted to start with calculus, you could take this coefficient of 1/2 and pull it out in front of the derivative here, but I'm not going to. What I'm instead going to do is take this 1/2 and distribute it into the parentheses to get rid of my parentheses. The 1/2 times the 2 just gives me 1, so I got the natural log of x. And then the 1/2 times x natural log of e gives me 1/2 times x times the natural log of e. But the natural log of e is just the number 1. Why is the natural log of e just the number 1? Because the natural log is always asking you the question, what power do you have to raise e up to make it equal to whatever you see over here? In this case, what I see over here is an e. So this is essentially asking me, what power do you have to raise e up to if you want to make it equal to e? This e right here. Well, e to the first power equals e. Therefore, the natural log of e is just 1. Therefore, I don't even have to write this right here. I can replace it with this 1. So this question, which started out kind of intimidating, figure out the derivative of the natural log of the square root of x squared times e to the x, wow, is really just asking me, what's the derivative of the natural log of x plus 1/2 x? That's easy. I don't need any chain rule at all. I got the derivative of a sum. Just take the sum of the two different derivatives. I could figure out the derivative of the natural log of x, and then I could add to that 1/2 times the derivative of x, pulling this coefficient out in front of this derivative. And these two derivatives are simple to take. The derivative of the natural log of x is just 1 over x. And since the derivative of x is just 1, I got 1/2 times 1. In other words, 1/2. What I'm saying is that g prime of x is just 1/2 plus 1 over x. It's really nice that this is so simple because the video doesn't end here. We're not supposed to just find g prime of x. We're supposed to then go on and find g double prime of x. Often when you're taking second derivatives, it's miserable because your answer for the first derivative is really ugly looking. And then if you have to take a second derivative, imagine trying to take another derivative of something that looks like this. It's really beneficial to simplify your first derivative when you have to figure out a second derivative. And by using all these log rules, I ended up with a really simple looking derivative. So now to figure out the second derivative, all I got to do is take the derivative of this thing right here. 1 over x I'll think of as x to the negative 1 power, so that it's really obvious which derivative rules I use. The derivative of x to the negative 1 is negative 1 x to the negative 2, and the derivative of 1/2 is just 0. So my second derivative is just negative 1 divided by x squared. Not too bad, right? But compare that with what would have happened, and I'll do this really quickly, if I had just taken the derivative of things the way they look right now, just flexing my muscles and using chain rules after chain rules. My outermost layer would have been this natural log, so I take the derivative of that natural log by making it 1 divided by, and then I'd leave all the stuff alone, so I got x squared e to the x raised up to the 1/2 power. But then I wouldn't be done. I'd have to multiply that by the derivative of all that stuff, x squared e to the x raised up to the 1/2 power. What's the derivative of x squared e to the x raised up to the 1/2 power? Well, chain rule, I'd first have to take care of that 1/2 power, leaving all the stuff alone. So x squared e to the x gets left completely alone. I have to subtract 1 from my exponent, so this becomes negative 1/2 up here. But then I'm still not done. I have to multiply that by the derivative of all this stuff, x squared e to the x. What's the derivative of x squared e to the x? Now you got to think about the product rule. The derivative of the x squared is 2x. You leave the e to the x alone, and then you add to that the derivative of the e to the x, which is just e to the x, and then you leave the x squared all alone. That wasn't too bad, sure, but that's just g prime of x, right? This is equal to this, but this is a hell of a lot easier to take another derivative of than this is. Imagine if you were staring at this and I was like, all right, now what's g double prime of x? That would be miserable, right? I mean, I could tell you what the answer is. It's this down here because this is equal to this, but it's not obvious that this is equal to this because we didn't take advantage of all those log rules. So the point of this second example was when you see some homework problems and it says something like, hint, use some log rules, it'll make your life a lot easier. The reason I'm asking you to do that is for this reason. So even if you walk into this class without these log rules, they're good ones to have handy and you can get some practice with them on the homework. When I was editing this video, one thing occurred to me. I had this example up here, right? And I asked you to find f prime of 3, and I didn't realize that when you plug 3 into the derivative, you'd end up getting an undefined output. And I was like, oh no, I've screwed up, but whatever, let it slide. I was just trying to demonstrate how to figure out f prime of 3. What didn't occur to me is I should probably investigate why 3 was undefined for this derivative. I mean, if you look at this function right here, there's no problem putting 3 in. 3 squared is 9. 9 minus 8 is 1. 1 cubed is 1. The natural log of 1 is 0. And the cubed root of 0 is just 0. This function is perfectly defined at 3. When you put a 3 into this machine, 0 comes out. If we looked at the graph of this function and we look for an x-coordinate of 3, we'd see a y-coordinate of 0. However, this function is not defined when x equals 3, as we saw by evaluating f prime of 3, right? We ended up dividing by 0. So how can that be? What would a graph look like where the function was defined at 3, but the derivative was undefined? Well, what I thought I'd do is show you just such an example. Not because you need to see it, but because it's kind of interesting. So I came over here to Desmos and I figured out y equals, I typed in this exact mess, and I took a look at the graph. And I found it pretty interesting. Here's the graph. First of all, there's all sorts of weirdness going on in the middle here due to the fact that you can't take the log of a negative number. But at 3, as we see right here, the function is perfectly defined. 3, 0 is on our graph just like we expected it to be. But what about the derivative? Well, remember what the derivative represents. The derivative is the slope of the tangent line to the curve at a given point. So picture the tangent line to the curve at this point. If you drew a line tangent to this curve, that line would be vertical. What is the slope of a vertical line? Well, it goes up 1 unit every time it goes over 0 units. The slope of a vertical line is undefined. So because the graph of this function becomes vertical at this point, the derivative of this function that we came up with an expression for down here is undefined at that point. The function's perfectly well defined at 3. Its derivative is not, because the tangent line would be vertical at this point, and vertical lines have undefined slopes. Maybe that's only interesting to teachers, but just in case that's interesting to you also, I wanted to add it on at the end. Thanks for listening.